Hey folks, in this video we're going to be doing some light maths. How juicy is that photon? You will be able to calculate that. So I want you to be able to calculate frequency using speed of light and wavelength. I want you to be able to calculate wavelength using speed of light and frequency. I want you to be able to calculate energy using frequency and Planck's constant. And I want to do some new vocab stuff like hertz, dimensional analysis, which we've already talked about actually, and joules will be coming up, and also Planck's constant, my dude Planck. Main equations we're going to use, there's really two main equations, and we'll get started with the first. The first is C equals lambda times nu. Speed of light equals frequency times wavelength. We've seen this before, but we're actually going to use it to do some math now. And it's actually more convenient if we rearrange this to solve for wavelength or frequency. So here we've got one of those, and here we've got the other one of those set to solve for wavelength or frequency. And so whenever we're doing math with this equation, we need to make sure that our units are correct. Because the speed of light is measured in meters per second, we need to make sure that these two units line up to make sure they produce meters per second when we multiply them together. So wavelength, we're always going to measure in meters when we're doing these maths. And this is often given to us in nanometers or other units, which is inconvenient, and we will have to convert into meters. Frequency, fortunately, is usually given in hertz or 1/seconds, and so we usually do not need to mess around with frequency too much before calculations. As we've said before, these units are also called hertz. So, and as I also mentioned before, we can rearrange these, but here are all the ways that you might see this equation. This is the way it's commonly written out, and here are two ways that are rearranged to solve for wavelength and frequency. Nifty, let's do some math with that. So our first example, we got a photon, it has a wavelength 5 meters, it's good size length. What's the frequency of this photon? So, first thing I'm going to do is I'm going to rearrange C equals wavelength times frequency if I need to. Then I'm going to make sure that my units for wavelength and frequency are correct, that they're in meters and 1/seconds or hertz. And then this may require unit conversion. And then lastly, I'll just plug it into my rearranged equation and solve for the unknown. So I rearranged this one already. We're solving for frequency, so we want to have it set as frequency equals speed of light divided by wavelength. My units are in meters for wavelength, so that's done. So now I can just plug into my equation. So I know speed of light because it's a constant, and I know my wavelength. So I'll divide the speed of light by 5 meters, and that's going to give me my frequency of 6.0 times 10 to the 7th hertz. Fun stuff. Why don't you help me out with this next one? So we have a green wavelength with a wavelength, green light with a wavelength of approximately 510 nanometers. What is the frequency of this green light? Well, first thing is I got to rearrange my equation. Same thing, I'm solving for frequency again, but my units are in nanometers, and I need to convert those to meters. Why don't you see if you can remember how to do this conversion? Cool. Well, you pause the video. What we're going to need to do is have a conversion factor. So with the conversion factor in hand, why don't you pause the video again and see if you can solve this now? Cool. Well, let's go through it together. So first thing we're going to do is do some dimensional analysis. We'll do our 510 nanometers, and we'll multiply that by a conversion factor. We're going to put the old units down below, so we're getting rid of nanometers. So we'll put nanometers down below in a fraction, and we'll put our new units up top. So we'll put the meters up top with this 1 times 10 to the negative 9th. And so when I multiply this out, my nanometer units will cancel out. I'll have nanometers divided by nanometers, and I'll be left with just meters. So I'll do 510 times this divided by 1 to give me my wavelength in meters. Very nice, very nice. And the last thing I should do is change this 510 so it's 5.10 for good scientific notation. So if I'm going to move my decimal place forward, I'm going to increase my coefficient by 2. So this is good stuff. If I move my coefficient forward 2, or my decimal place forward 2, I'm going to increase the coefficient by 2 from -9 to a -7. Cool, so I converted into meters. Well, now I'm set to just plug and chug like the last one. I'll do the speed of light divided by my wavelength. And so that's going to give me a fabulous answer for frequency of 5.88 times 10 to the 14th hertz. Cool, let's try one more. And I'm going to ask you to just do this one on your solo. So here we have a photon. We know its wavelength. I want you to solve for the frequency of this. This one is in kilometers, and I have a conversion factor for you here. So why don't you pause the video and try this out now? Cool. Well, let's go through it together. First thing I need to know is the correct equation. So I'm going to use that lambda equals speed of light divided by frequency. And I'm going to need to convert these kilometers into meters. So to do that, I will start with the number I want to convert, and I'm going to multiply that by my fraction, and in the fraction will go my conversion factor. The old units should go down below, so I'll put 1 kilometer in the denominator, and I will put 1 times 10 to the third meters in the numerator. And so now when I multiply these together, kilometers will cancel out, my units will be left in meters. So I'll do this number, 3.3 times 10 to the negative 6 times 1 times 10 to the third, and that's going to give me 3.3 times 10 to the negative third meters. Cool. So now I can just plug this dude in to my fancy pants equation. So I'll do the speed of light divided by this number, and that's going to give me my frequency of 9.1 times 10 to the 10th, times 10 to the 10th. Yeah, hertz, or inverse seconds. Fun stuff. Well, look at this cat. This cat is super afraid of these two fuzzy buns. What? They're fuzzy buns. Cat, you're supposed to be a predator. You're bad at being a predator. Anyway, the second main equation that we're going to use relates energy to frequency. And so this is my energy equals Planck's constant times nu, or frequency, my little v, which we sometimes call a nu. And so here it is written out in words. And what is Planck's constant? Well, it's a constant, yes. And here are the units for it and the number. It's kind of got interesting units. It's got units of joules times seconds, and it is this really tiny number, times 10 to the negative 34th, very small number. So energy, when we talk about this, we're mainly going to be talking about energy measured in joules. That is pronounced like jewels, the precious jewels, which I might wear around my neck if I were, I don't know, some dude who wore jewels. But it's spelled a little bit differently. And so occasionally we may see some other versions of joules like kilojoules or megajoules come up, but joules are the main unit that we are going to use when we are talking about energy. So we can also rearrange this equation here. If we wanted to solve for frequency instead of energy, we can rearrange this so that frequency is equal to energy divided by Planck's constant. And if we were really fancy, we could substitute into this equation frequency. Instead of frequency, we know frequency is equal to c divided by lambda, so we can substitute this term in instead of v, which gives us this equation here. So if we want to convert from wavelength directly to energy, we would use this equation here. Neat. Well, let's try doing some problems with that. Why don't we? So a photon has a frequency of 5.00 times 10 to the 17th hertz. What is the energy of this photon? So I'm going to use my fun E equals HV equation. The units are already correct. I need to make sure that they are always in 1/seconds or joules when I use this. So I can just plug right in. So I'll do my Planck's constant times my frequency, and easy peasy, I come up with my answer in joules. Shazam. Let's look at another problem. So here we have a photon which has an energy of 7.6 times 10 to the negative 8 joules. What is the frequency of this photon? Why don't you pause the video and using that E equals HV equation, try to solve here. Cool, well, let's go through it together now. So I'm going to rearrange that so that because I'm solving for frequency, I want to have frequency isolated. So I know frequency equals energy divided by H. And I have my units, they're already in joules. So all I need to do is plug into this equation. And I'll plug my joules in and divide that by Planck's constant, which are some ugly numbers, but it works out. And we get this fun answer of 1.15 times 10 to the 10th as our frequency. What kind of light is this? Using the spectrum, the electromagnetic spectrum provided down here, why don't you pause the video and think, what kind of light has this frequency and also this amount of energy? Cool, well, you paused it. We can look at this and see up at the top are our frequencies. Our frequency is approximately 1 times 10 to the 10th. And in that 10 to the 10th, that would make this a microwave. Very fun. Microwaves. Very useful for heating up food. Fun stuff. Well, let's look at some more problems. Here we've got a photon that's got a wavelength of 4.8 times 10 to the negative 5th meters. Why don't you try and calculate what the energy of this photon is using the equations we've already talked about. Sick. Well, you've tried that out. Let's go through it together. I'm going to use that real fancy pants equation equals H times C divided by lambda. And all I need to do here is plug in. And you know what? This is silly. This is a mistake. This should say my units are in meters because I'm looking at wavelength. And when we are working with wavelength, we want to have our units in meters. Our units are in meters, so we are good to go. So I can just plug into this equation. So I've got H divided by my constant C divided by my wavelength in meters. I'm sorry, H times my constant C divided by my wavelength in meters. Important not to mess that up. And so once I plug all this into my calculator, I get a fabulous energy of 4.12 times 10 to the negative 21st joules. Cool. I hope you came up with the same answer. Let's look at one final problem. Why don't we? So here we've got a photon with a frequency of 8.21 times 10 to the 15th hertz. Why don't you pause the video and try and come up with, first, what is the wavelength of this photon? And secondarily, what part of the electromagnetic spectrum does this photon belong in? What kind of electromagnetic radiation is this? Pause the video and think about those. Yeah. Cool. Well, going through it together, I'm going to rearrange this so that I have wavelength equal to speed of light divided by frequency. And I'm going to say, all right, frequency has the correct units of 1/seconds. So I can just plug right into my equation. And that's going to give me a wavelength of 3.65 times 10 to the negative 8th meters. Well, I'm then going to look here and say, that seems like that would probably be in the ultraviolet. And 8, this is very close to 1 times 10 to the 16th. So yeah, this seems like this would be ultraviolet light. Cool. Well, that is the end of this video. I hope you feel like you can do some math involving photons and do calculations about photons. And yeah, I hope you have a great rest of your life. Ta-ta.